So I will discuss the safety formats. Safety formats that we can use when we perform, or when we try to apply these more advanced methods in practice. So as engineers, we all know that we always have to deal with various uncertainties. First of all, we are not sure about the exact properties of our materials. Dimensions may not be exactly as they were in the drawing, and so on. So we always have to put our results or calculations into some safety format. So this will be the topic of my presentation today. Just to give you a background about myself and what our company is doing. So basically, for last 20 years, we are developing technologies and also, of course, software codes for nonlinear modeling of concrete structures. Okay, so just to lay the background, I just want to show one example. So this is from a real project in India. So at the top, there was this very thick slab with some connected steel elements. And of course, to design this and even to check such a design, the standard tools are, let's say, very difficult to apply. So nonlinear analysis was used to check the design, and the nonlinear analysis then performs typically in the following way: that we create the model with the proposed idea of the reinforcement, and we then apply the loads until failure, as you see now on the slide 43. I hope you are seeing it as well. And then, of course, when we calculate the failure, we have to compare with the design load level. And now it's a question, what should be the safety factor? So we are using nonlinear method. That means we divide our model, or in most cases or typical situations, of course, there are other methods that can be used, but I think most engineers nowadays use finite element method. So we divide the structure into finite elements, and inside the finite element, we are assuming nonlinear behavior. So our analysis typically works as shown in this graph at the bottom left corner. So we have to load the structure by steps, and at each step, each step always involves a predictor phase where we assume linear material behavior. We calculate the stresses at this point 1. And of course, we check the stresses with respect to the material criteria. And if these criteria are violated, we have to reduce the stresses. So we basically jump to step 2, to the state 2. So that means at this point we are violating the equilibrium. So the forces in the structure are not equivalent to the applied forces. And an iterative process is used to redistribute these stresses to the rest of the structure. So this is very brief summary of the principles of nonlinear method when applied in finite element analysis. I will be also showing some examples. So this is, let's say, the material models which we used in those examples, but we have to understand nowadays there exist various material models for concrete, for steel, for soil. They are typically based on plasticity, damage mechanics. Orthotropic smear crack models are very often used in the commercial programs, or there are some more modern microplane models. So typically we are then assuming some kind of stress-strain uniaxial law. As you can see here, we know that concrete in tension is very brittle, and then there is some softening. But how we handle this softening is very important. I will come to that later. In compression, we have the nonlinear behavior up to compressive strength, and again there is a softening. People often forget that actually that there is a softening also in compression. But in typical situations, we have to think about two-dimensional or even a three-dimensional state of stress. So we have to use failure criteria which accommodate the biaxial or triaxial state of stress. Well, I told you that in terms of these brittle materials, like concrete in tension, we have this crack occurrence, and when crack occurs, it doesn't mean that the stress immediately drops to zero, but it is known that there is some kind of softening relationship, and this energy dissipated under this crack opening law is called fracture energy. So it is one of the important parameters. And it actually, similar situation is also in compression. This is, let's say, quite known from physics, that to break a material, it's not so important to provide the force or to provide the stress. Important is to provide the energy. So these energy-based principles are very important to be incorporated into any finite element analysis which is being used for these kind of brittle materials, like concrete. So let me now talk about these safety formats available for nonlinear analysis. The formats that I will be presenting are part of the FIB model code, which was proposed in 2010. And actually, they are used as a kind of a model approach to developing the new generation of Eurocodes, which was mentioned previously by Steve. So let's just make first some kind of basic comparison. So if you think about how we work today, we typically perform a linear analysis of our structures, and then we check the critical sections and check whether the internal forces in those sections are smaller than the design strength. And here is a little, let's say, discrepancy that typically we perform linear analysis to calculate the internal forces, but to calculate the strength of our section, we usually assume that concrete is cracked, reinforcement is yielding, so we assume a highly nonlinear behavior. So this is a small, let's say, discrepancy. On the other hand, it is simple and very robust and a very verified way of working. So if we come to nonlinear analysis, things become a little bit more complicated, and this approach is not so suitable. So typically what is being done is that the load combination which we want to investigate is applied to the structure, and we calculate the failure load, and this global failure load should be then, of course, this calculated failure load, which is the R global, like G, and D meaning the design. So this is like the strength of the structure, and then it can be compared with respect to the applied load combination. So it should be, of course, greater than the applied or the ULS load combination. So typically, this equation is like this, as we showed on the previous slide. So the design load combination should be smaller than the strength of the structure. And now, how we calculate this the strength of the structure, this RD. So this we can calculate by performing some nonlinear analysis, and then we have to apply some safety factors. So one safety factor will come from the material uncertainty, that's the gamma M, and the gamma RD would be the uncertainty of our model, because we have to understand that this our nonlinear analysis is of course a model. So this is not reality. There are some uncertainties involved. And I will discuss 4 safety formats which are proposed in the FIB model code. And of course, not all of them will appear in the new generation of Eurocodes. This is, let's say, still under discussion. Most probably this PSF method and this ECOV method will appear there, but this is, let's say, still not fully clear. So let me just summarize the principles of these 4 methods. So the first one, which I call PSF, or partial safety factor method. This method is a kind of a natural extension of how the engineers are working today. So in this analysis, we make a nonlinear analysis, and in this nonlinear analysis, we use the design material parameters. That means the material parameters which are multiplied by the design factors. I mean, by the partial safety factors, yes? So for concrete, for instance, 1.5, for steel, 1.15. And in this nonlinear analysis, we can directly assume it is like an estimate of the design strength. The second method actually is already present in the current codes. It is in the Eurocode for bridges. There we assume that we calculate kind of a nonlinear analysis, which we can say is a mean analysis, average analysis. But we are using average properties of steel, but concrete properties are calculated from FCK multiplied by 0.85. So this is an interesting method where this allows us to use a single safety factor, global safety factor of 1.27. Then the third method is ECOV method, which was proposed by my colleagues in our company recently, where we make two analyses. One analysis using mean parameters and one using characteristics. And then we can estimate the global safety factor using the standard assumptions of the code, the reliability, and so on. So, but this approach requires two analyses with mean and characteristic values. And there is the fourth method, which is, let's say, full probabilistic analysis. I'll come to that later. So if we now look at what it means in reality, so the probabilistic method is that you actually assume random distribution of the materials, you perform many analyses, and you exactly then can evaluate the probability of failure, and out of that calculate the design strength of the structure. Such methods are nowadays possible, but of course very demanding, and let's say not applicable for daily engineering work. Kind of a simpler method is this ECOV method, which already somehow considers the probabilistic aspects. That means we perform analysis with mean parameters, we calculate RM, then we perform analysis with characteristic parameters, and we say this is an estimate of the characteristic strength, and then we can use these two values to assume the distribution, to assume that there is a log normal distribution, which is usually the case in reinforced concrete structures, and we can directly then estimate the design strength. If we compare it to this global approach, there we estimate the mean value and we directly make an assumption of the design strength. And this can be also contrasted with this partial safety factor method, where we directly calculate, or we assume that we are estimating directly the design strength. As you can see in these last two approaches, we have no idea about the distribution. However, we consider the distribution by these partial factors directly applied to the materials for this PSF method, or by this global safety factor for this global safety factor approach. So this is again a little bit more explanation about this ECOV method, which is a method which with quite high probability may be implemented in the new Eurocodes. So with this analysis, or with this method, we perform two analyses. In one analysis, we use mean average material parameters. Another analysis, we use the characteristic material parameters. And we say these analyses give us an estimate of the strength characteristic and mean strength. And then we can assume log normal distribution. Of course, this log normal distribution is, let's say, an assumption, but we know that for material failures and brittle materials, such a distribution usually happens in reality. And from that, we can estimate using the reliability indexes as defined in the Eurocode 0, the basis of the Eurocodes, and we can make assumptions. I told that we can calculate the design strength. The advantage of this approach is that you can consider different betas. If it is an existing structure or a new structure, if for some reason you can justify lower reliability indexes for particular structures. Yeah, this is a summary of this Eurocode approach currently in the bridges. Bridge Eurocode, I think I will skip this one. Basically, this method has an interesting idea that to allow for a single global safety factor, we somehow shift the material parameters that we use for concrete. For steel, we use the average values. For concrete, we use somehow reduced values. And this allows us to use a single global safety factor, which otherwise would have to, of course, depend whether the failure is in concrete or whether the failure is in steel. Well, let me now show some results of comparing these various formats for different models. We published about 5 years ago a paper on this topic where comparing testing how all these methods behave for different structures, starting from simple bending problems up to more complicated shear problems. And if you can see in the table, the numbers are normalized with respect to the PSF method. These are the values of the design strength. And if you see at them, look at them, you kind of see that the methods which are, let's say, more, first of all, if you look at the first 5 examples, or first 5 examples, yes, there you see a very little difference. So all the methods are somehow give similar results. The percentage, there's just few percentage difference, which I think we can neglect. For some of the lower problems, you suddenly see that these probabilistic methods or semi-probabilistic methods, which they give slightly higher design strength, which of course can be explained by the fact that some more knowledge is implemented about the distribution of the material. Here are some of these examples which have been used. So we use also shear examples, modeling a shear failure. On this slide, I want to also indicate what it means to make a full probabilistic analysis. In case of full probabilistic analysis, this means that we do not make a single analysis, like let's say this solid line corresponding to the experiment, but many analyses, kind of a Monte Carlo simulation. But there exists some smarter Monte Carlo methods, so-called stratified methods, which can limit the number of necessary analyses. But still, in the simplest case, at least 30 nonlinear analyses are necessary. This is a summary of this ECOV method for this example of a shear beam. And there you nicely see that the methods give very meaningful results. The PSF methods, which is, let's say, most conservative, gives the lowest design strength, and the one which is most sophisticated, like the full probabilistic method, will give you slightly higher tensile strength, design strength, I'm sorry, shear strength, basically, in this case. So in this particular example, things work very nicely. Of course, there are some situations which have been reported where these methods don't behave that nicely, and this is still under discussion, therefore. Just for your interest, here you, for instance, see where are the formulas for this beam from the current Eurocode and, for instance, from ACI code. So we can also see that even in the current formulas, we have, let's say, problems in some particular situations of very deep and lightly reinforced beams failing in shear. Well, let me now give at least some information about how to evaluate the uncertainty. Yes, because I told you before, we have to understand that nonlinear analysis has some uncertainties involved by itself. So we need to, the best way how to evaluate this uncertainty is to compare with experiments. So we need to make it is important to perform such testing and evaluation. And this, I'm presenting here for one particular study, which involved 33 cases. Of course, this study is valid only for the numerical model or the software or material model, which was used in this study. You cannot extend that to other programs. And in my opinion, such studies should be performed every time somebody wants to apply nonlinear methods. Either it should be performed and validated by the software developer or the engineer should do it himself. So in this case, we have 33 cases, 15 from punching shear, 7 from shear strength of large beams, 11 from bending strength. So it covers, let's say, quite representative cases, quite representative set of problems. Very important thing for these evaluations is to have a clear definition of the input parameters. You have to understand, and maybe some of you have used nonlinear analysis, so you know that there are usually many parameters, but as engineers, we usually know only compressive strength. So it is important that there is some clear set of rules defined how from compressive strength all the other parameters are estimated. And if there is no estimation or no clear rule given, then some default values should be used in the whole study. And okay, we cover quite a large range of problems from high strength concrete, normal concrete, brittle failure, shear failure, and with different sizes. This is the material parameter, the material model which was used. One example, just to give you an idea, where these punching shear problems from Zurich and from Sweden. Here is just one animation of such a punching analysis to give an idea of this nonlinear process. Here you see some results, and as you see, the results are not always perfect, yes, because the material parameters are always generated typically from the compressive strength, which is the only value, only parameter which is typically given. Another example are these various shear beams. One of them is this very large beam from Toronto. Here you see also the prediction of the shear failure. So you see the peak load was quite well predicted, although it is a little bit higher, in about 7–8% higher than the measured one. On the other hand, we have to understand that this was a, let's say, single experiment, so we cannot say it's the average or the mean experiment. But there were other beams also tested with different sizes. Important was also these bending beams, and they were also quite interesting and giving a large representative range of problems. Some of them fail by reinforcement, some of them fail by concrete crushing. And this is, let's say, the result. Yeah? So when we evaluate for this particular situation, we obtain that for shear and punching, the uncertainty is a little bit higher, and the safety factor should be 1.16, 1.13. For bending problems, the uncertainty is much lower. Well, there have been published similar papers by different people and softwares used, and they actually provided similar results. But still, my opinion is that such a study should be performed for each software or model separately, and should cover the representative range of problems. In my opinion, also engineers who try to apply these methods, they should make such a study to cover the cases he's using to determine this uncertainty factor. We also tested this for crack widths, because nonlinear analysis is also a very interesting method to check the service limit states, where one of the important parameters would be the crack width. And we can see here is a study. It is not so extensive, on a little bit limited set of examples. And here you see a typical result of such an example. You see it's a 4-point bending beam, so the middle section has a uniform moment, but still the nonlinear analysis can predict some crack spacing and crack width. So this is then interesting to evaluate. And we also have published a paper on this topic, and the final result was that it was possible to predict the maximum crack, but let's say the mean crack was over-predicted. So this means also that the nonlinear analysis was not able to capture the scatter. And that's mainly because in the nonlinear analysis that we use, we have not considered the fact that we have a random distribution of material parameters, which of course changes this situation. Okay, so I would like to conclude my presentation. The conclusions is my conclusions are that there are some safety formats available nowadays for nonlinear analysis. I would say, I think Model Code 2010 is, let's say, the first code which have some proposal for them, and hopefully these methods will also appear in the new generation of Eurocodes. In this respect, I think this PSF method is quite natural method, which is quite natural for engineers. It's a natural extension of the current partial safety factor method, which is being used. But of course, we have to pay attention to model uncertainty. And this was also mentioned or described very much by Steve. And so to determine this model uncertainty, validation by experiments is necessary, and it should be performed for the range of problems where the nonlinear analysis is then will then be applied. Well, for the test we did, we calculated this model uncertainty factor to be 1.16. But again, I have to emphasize that this factor should be really model dependent, well, maybe even engineer dependent, yes. But at least we can say if the engineers follow some guidelines, then it can be model dependent. It is also possible, or interesting application of nonlinear analysis is also for service limit states, for deflections and crack width. And we are seeing that it is possible, and it provides very interesting results. So thank you for your attention.
I think I'm just going to ask one question, which I think sort of encapsulates what some people are asking. And that is, you've picked up on actually various bits of software and models vary. Is there anything to sort of standardize that or enable you to sort of use a piece of software with confidence for nonlinear analysis?
Is this a question?
It is a question, Jan. Yes. Sorry if I didn't make that clear.
Yes, of
so
course.
Sort of, people are just concerned about how you actually apply it. What sort of limitations there are, and are there national directives or national guidance on using different models or different pieces of software?
Well, it is very difficult to define one guidance that will fit all. Yes. So I think the current trend is to define, let's say, a simpler guidance, because the codes doesn't have to, and there is no room for all the details. and provide some guidance on this validation process, so that this validation process should be performed.